The next exercise is about electrodynamics, in which we try to reformulate the various expressions for example, the electromagnetic tensor in terms of two forms. And again, so this is an exercise to experience and try out two forms in an environment that perhaps you are confident about, meaning electrodynamics. Okay, so let's start. As usual, try to put on the paper all the information that you find written in the questions and in the description of the exercise that you're going to solve. So we are in spherical coordinates, so you can write down the coordinates that you're going to use, time, radius, and then the two angles. And that's to remind you better in a more clear way than all the terms that are going to enter in the sumatories and the relationship with the one forms, coordinates, and so on and so forth. Then in the exercise is given to you the four vector, or in this case is given you in the dual basis set because the indices are lowered. And that's the guy. So you see, this is the coefficient theta for the phi component. Sorry, the coefficient phi for the phi component of your one form. Therefore, your full one form reads in this way. So 0, 0, 0, and then you have this coefficient that is only for the phi component. Okay, so that's the four dual vector of your what is going to be then your four potential, vector potential of electrodynamics. Then we start with exercise A, so that's the first point, in which we need to compute the Faraday 2 form. And basically, we need to apply the RAM operator to A. Okay, so A, we know the definition of the RAM operator we have already seen already, so what we need to do is just to apply this expression, the one that is asked for. So we plug in A, then you have it from here, okay. Only the phi component is available, so that's this one. And then we apply the definition of the RAM operator, which is this derivative with respect to nu, dx nu, okay. So that's the RAM operator, which is again I just write it here for your convenience. So that's the nu, the x nu, okay? And then this is combined if there are other bases with the wedge operation, with the wedge product that you find here, okay? Good. So we therefore apply the derivative to the function that is expressing with A, therefore the derivative of the coefficient, that's the coefficient, derivative of the coefficient, and then the x nu, again from the RAM operator, that then combines, the x nu combines with the phi, which was already present in the definition, in the basis of the form. Then what we need to do is we have all derivatives, these are repeated indices, but therefore we have a summatory of those derivatives, and we have to look for the derivatives that are of interest. You see that we have this function, the variables are r and theta. Therefore, the derivatives are going to be with respect to r, that we have here, and theta, that we have here. Okay, so therefore we are going the phi, which is the r, the x phi, which is the r. Summatory, the other derivative, which is non-zero, is for theta, and we have the theta. That's it. And then we just apply the derivative, and we have the final result. So this is the final result of the question. Okay, you should stop here. In the exam, you just stop here. Now, just to give you further information and let's say, refresh also the connection with the formulation that we are used to, we can just make the connection with the energy momentum tensor of electrodynamic that is based not on the wedge operator but on the standard interior operator. Nice. So let's do that. So we have this expression. What we can do is to make explicit, use the explicit definition of the exterior product. Okay. So we just do that. And the definition of the exterior product for the phi and the phi is this one. The exterior product for the theta, the phi is this one. Okay? And you see the minus that enforces the antisymmetry on the final tensor F. Then what we do now, I'm just working out this one because this guy is identical. So if I just work out this term, we just have this one minus this one, which is that. Okay. Then what we have, if we know that we can express that this is an expression of the mu nu times the x mu dx nu, right? It means that this guy is the coefficient f theta r, right? Therefore, f theta r is equal to minus f r phi, and here you see the antisymmetry. If you do go the same exercise for the other one, you are going to realize that there is antisymmetric. The tensor is autosymmetric also for the other non-zero component. And that's the standard expression, so that's what you would expect for the electromagnetic tensor of electrodynamics. Now, if you want, we can do the things the way around. So we can start with what you are used to. So in electrodynamics, we have always been working in this way. And to enforce the antisymmetry on this tensor, what was done was not to use the exterior derivatives, as it has been done here, but by creating an electromagnetic a tensor which is by design, by construction, antisymmetric. And one way to create a tensor which is antisymmetric is to use a four vector. In this case, with the lower indices is a one form. Sorry, in which for a dual vector constructed in this way. Okay, so let's try to give a look if we get the same result as we obtained up here. And let's try out. So we just use f mu nu as we created in this way. So we just plug it in, and we obtain, once we apply the symmetries, we have these two terms, right? Two terms because we have the derivative. We have only an r and phi component, so only two derivatives are going to appear for this term and this term. Then the phi over a of r is equal to 0. That's because er, which is this guy here, is equal to 0. And the derivative of phi of ar, again, is equal to 0. So these two terms cancel. We are only left with this, and look, is exactly what we had in the previous derivation. So you see that we have these two coefficients that identifies with these two guys. I mean, that's what we got before, okay? Perfect. Nice. So that's it. So the meaning, then this is going to be our for the equivalent to the four potential. That's our four potential vector dynamics, and F is indeed our energy momentum tensor.